Hello, welcome back to section 6.6. In this video we'll be going over example 2. So example 2 is a machine. A lot of times machines will have pulleys so that they can move. That's basically the biggest difference between a frame and machine, is that machines are designed to move, frames are designed to not move. So because they have pulleys, a lot of times we're going to be needing to cut through these ropes. So remember that ropes only hold tension, they can't hold compression or any other forces. So when you cut through them, you're going to get forces equal and opposite on both sides. That's one of the keys to analyzing a machine. So I've drawn this up over here on the paper. Alright. Oops, there we go. A little bit of lag. So we have our pulleys here. Sorry about that. We have our bar AB. We have 6 kilonewtons down here. We have our pulleys. So between the centers of the pulleys, it's 0.9 meters. The pulleys are 0.1 meters in diameter. We're asked to find the force P needed to lift this bar, and also the distance x such that we remain in equilibrium. So to do that, we need to kind of disassemble this machine so we can do some analysis. So I've done that here. I've redrawn bar AB, and I've sliced through the ropes. So I sliced through here, and I've sliced through here. And that created this tension. So we would have had a tension and a tension come out of that. And so we've drawn the bottom one here. There's another piece of rope here. And then for B down here, we cut through this rope, and we know that it's P because we have the pulling force on this side, which means if we follow this rope, it has to be the pulling force on this side. Because I cut the rope, these also have to be equal and opposite in direction. So we know that this is P. Then for pulley C, we've redrawn that. So again, we already had the pulling force on the right-hand side, and so now this is the cut that matches up with this piece. This rope, so I went ahead and cut it here as well. It'll snake around, but we don't care about the top part of this rope for this analysis. So the first thing we're going to do is we're going to use this pulley to create a relationship between T and P. So we can do this with one equation. So sum of forces in the y direction, I'll assume up is positive, equal to 0. So we have 1 T going up, we have 2 pulling forces P going down, equal to 0. So now we know that 2P, P, not T, is equal to T. That means when we come over here, let me kind of separate this. So that's kind of its own little area. So that means when we separate, come back over here, we can now sub in, and we will reduce the number of variables that we have here. So if I do a sum of forces in y for this problem, initially what I get is I have T and P going up. So I have a positive T, I have a negative 6 kilonewtons, and I have a positive P, all equal to 0. So I have 2 unknowns, but because I have this relationship over here, I can sub in. So I don't care about finding T, so I'll sub in for the T. I'll have 2P. So when we simplify this, we get 3P is equal to 6K, which means that P is equal to 2 kilonewtons. And so that answers the first part of the question, how much force. So anything larger than 2 kilonewtons will lift the beam. And now we need to know how far over does this 6K need to be in order for the beam to not rotate, because that's what will happen if this isn't positioned correctly. So we can do that with a moment equation. So again, we don't care about finding T, and x is measured from A, so I'm going to do a moments about A. So we do sum of moments about A equal to 0. So we don't need T, and the X is measured from there. So we're going to get the 6K times X plus, and that is going to act in the, negative direction. I need to put a negative sign on this. So remember, determine your senses manually, so that's going to go around this way, which is opposite of what we are assuming is positive. And then plus P, and P, so we need to determine what the distance. This is one of the things that people get wrong on this problem. So if we start over here, and we come down, so that goes down to point B, right here at the center of this. And I go 0.9 over, so I go 0.9 over, and I go one more radius of this, which is 0.1, so 0.9 plus 0.1. So 0.9 plus 0.1, so that's 1. And that is going to create a positive moment as we've defined it. So that'll all be equal to 0. So we have two unknowns here currently. We have X and P, but we've already found P to be 2 kilonewtons, so I'll sub that in. And so we'll clean this up. We're going to get an X is equal to, so this is going to be 2K times 1. So we're going to end up with a 2K. And then this is going to be a 6K. We're going to divide that under. So negative 2K over negative 6K. The K's will cancel. We'll get 1/3 of a meter, or 0.3. So yeah, 1/3 of a meter is our answer there. So a third of the way over. All right. So again, the key is to be able to cut through these ropes, realizing that you have the same forces on each side. So again, tension here, P here, and P here. If you have any other questions, feel free to contact me.